One of the architectural decisions that's central to Mongo is the ability to scale out horizontally. In other words, to add additional servers to increase the capacity or the throughput or the reliability of the database, as opposed to scaling up vertically, where you're trying to buy a larger and larger, more capable single server. One of the advantages of the scaling out approach is that the servers that you add to the cluster that's maintaining a database are going to be less expensive, easier to maintain, easier to replace. But on the other hand, they're also going to potentially be more likely to fail. And so in order to increase the reliability of a database when you're using rather more modest servers in larger numbers, one of the key characteristics of the database to make that work is to provide a replication mechanism. So the idea here is that we want to be able to create multiple hosts for the database that can store the information in the Mongo database redundantly. So we're going to have multiple copies of the same data at various machines in our cluster that's providing the database service. And if one of those goes haywire, the system can kind of heal itself and begin serving information and storing information using a different subset of those servers that are configured into the database. By way of introduction, then, let's take a look at some of the terminology that we're going to employ. First of all, the key idea here in Mongo is a replica set. What that is, it's a group of MongoD instances. And I haven't really talked about MongoD so far. That's a common convention in Unix and related operating systems like Linux to have server processes that are basically long-running processes that are constructed at the time that the system boots up and that run for the duration of the time the system is available. So things like the SSH server or the email server, or in this case, the Mongo database server. So server processes are usually referred to as daemons in the operating system, and to distinguish them from other types of processes, the convention is to give them a name that ends in D. So, for example, the SSH daemon that is the server listening for inbound SSH connections is usually called SSHD. And we've got a similar kind of a convention going on here where the Mongo daemon that is running the Mongo database and listening for connections is referred to as MongoD. You might read it as Mongod, but it's really not intended to be read that way, I don't think. So when we're running a Mongo process, a Mongo server process, we're running an instance of that MongoD daemon. And what we're doing when we create a replica set is we're going to run multiple of those MongoD instances that are going to be connected basically to one another in order to manage the same set of data. And of course, if we put those MongoD instances on multiple independent servers, then we have the possibility of allowing for that set of servers to recover from the failure of one of the members of the set and take over the responsibility for managing the data. So this design is intended to provide some redundancy. In other words, the ability for one of those nodes to fail while others take over. And the result of that is high availability. In the face of failures of complete servers in that configuration, the outside user of the Mongo service may not even be aware of the fact that something went haywire inside, because from the outside world, it appears as if the database is just continuing to operate properly. And this, of course, is going to be kind of the basis for any kind of a production deployment of Mongo. You don't want to rely on a single server, a single point of failure, particularly when you're running on servers that are maybe less capable than you might run if you were trying to do a vertical scalability approach. Now, within this replica set, there's two types of nodes that are distinguished. The first one is called the primary node, and it's basically the kind of the center point for interaction with that set of nodes in the replica set. One of the things that's really important here is that this is the node that's going to receive all of the write operations that are being sent to the database management system. You could see that if we have multiple nodes in the replica set that could potentially themselves receive operations to write to the database, to make changes to the database, that we might run into some problems with race conditions. Right? If I have two or more nodes that are designated as allowed to write to the database, then the one that gets there last is going to win, right? If we attempt to overwrite or update or add information through both of those servers. So the solution that Mongo takes to dealing with that race condition is to just say there's going to be only one designated node in that replica set, one designated server that is going to be responsible for doing all of the write operations. And that way you don't have the possibility of multiple attempts to update or insert the same data. Every other node in the replica set pretty much is going to be then called a secondary node. And its main job is going to be to replicate the contents of what's being stored by the primary node. And of course we could have multiple instances of these secondary nodes, and we'll see kind of how that works here in a second. Here's an illustration that I've lifted from the Mongo documentation that gives you a little bit of a picture of what a replica set might look like. First of all, on the top here, we've got the client application. So this is the program that we're writing that needs access to a Mongo database. And it's going to interact with Mongo through some sort of a driver. So the C driver or the Java driver or the Python driver. And there's going to be, of course, two types of requests that could be made to the database by the client application through the driver. Either we're going to write information to the database by inserting something new or updating something that's already there, or we're going to issue a read request to get stuff from the database. As illustrated here, both of those kinds of operations are going to be sent to the primary node in the replica set. So if you're going to write something to the database, the primary node is going to be responsible for storing that somewhere on disk. If you're going to read something from the database, that's also going to be the job of the primary node to fetch information from the database. Now, behind the scenes then, in order to provide this notion of replication and high availability, the primary node in the replica set is going to be interacting with the additional nodes, the secondary nodes that are configured into that replica set, and basically pushing information out to them to make sure that the copies of the data that's being maintained within this replica set is consistent across all of the nodes in the Mongo server. Again, because we're only going to be allowing the primary node to do writes, we don't have any race conditions here. There is a possibility, of course, that because the replication process itself is not going to be instantaneous, that we might have a situation where the primary has slightly more current data than the secondaries until the secondaries replicate from the primary and themselves receive any updates that were received by the primary. As long as everybody's functioning normally, this is going to work just swimmingly. The primary is going to continue to service the requests from the client applications and also sending updates to the secondary nodes in the replica set so that they can remain up to date. But of course we want to make sure that this thing is going to work properly if something goes wrong. So let's take a look at a mechanism that's used to, first of all, detect that something bad is happening. You can see here in this illustration, also stolen from the Mongo documentation, that I've included some additional connections here between these nodes that I've labeled as a heartbeat. The basic idea of a heartbeat is that every couple of seconds or so, and that's configurable, I believe, the different nodes are going to send a message to one another to basically say, I'm alive. And then a few seconds later, they're going to send another message that says, I'm alive. So on a very, very regular basis, the different nodes are going to be letting each other know that they're there. And if one of those nodes kind of drops out of the picture, let's say a secondary node crashes for some reason or goes offline because of network connectivity issues or something like that, then the replica set is going to act to remedy the problem that it apparently no longer has access to one of the nodes in the replica set. And this is how Mongo facilitates this ability to fail over. The first thing to note about that process is that, as we saw back here on this slide, the primary node is really driving the bus here. As long as the primary is available, all of the clients that are hitting this particular database are going to continue to operate just fine. Whereas the secondary nodes are really present for providing duplication and backup and redundancy. So if we have a situation where the heartbeat, say of this secondary node disappears, it's not really the end of the world, right? Because the primary can continue to function in the role that it's supposed to have, answering queries from the clients over the drivers. And at some point, maybe that secondary node might come back up, and at that point, then the replica set could synchronize that new secondary node with the data that might have been changed since it was the last part of this replica set. However, if it's the primary that goes down, that's a problem, right? We now have no way of servicing the requests from applications clients that need access to this Mongo database. So here's kind of the protocol for what happens when the primary node disappears. It's called failover. So if the primary doesn't communicate for more than 10 seconds, again, that's the default timeout, then the secondaries, who will by that point be aware that the primary has disappeared, are going to do what's called an election. And the goal of the election process is to determine who's going to take over for the primary node. One of these secondary nodes, which has received all of the updates and changes from the primary, except for perhaps the very, very, very most recent ones, are going to have all of the state in the database stored locally. And so at any moment, one of those secondary nodes could step in to become the primary. So this election process results in a determination of a secondary node that's going to become the primary. So the first secondary to hold the election, and it's going to get a majority of the votes from the different nodes in the replica set, becomes the new primary. So we've got a picture of that here. We're showing that the primary node went down, is no longer participating in that heartbeat exchange, but the secondary nodes are still working, and they're sending their heartbeat information to one another and recognize that each of them is continuing to function normally. And if this state persists for more than 10 seconds, the secondaries are then going to hold an election. They're going to trade some information back and forth according to a well-defined protocol that leads them to conclude, collectively, one of those nodes is now going to be designated as the primary node. And that's the state we're illustrating down here. So this node, which was a secondary node, is now going to be the primary node, and all of the requests from clients are going to be redirected to it for both reads and writes, and then it will be replicating to the additional secondary node or nodes that are remaining in the replica set. There's one other wrinkle here in the replica set model. Because a primary could fail at any time, the basic idea is that the secondary nodes have to be running on servers such that they could step in and take over the job of the primary, which means that those secondary nodes have to be quite capable servers. Another thing that those secondary nodes are doing is kind of managing this heartbeat failover algorithm. And that portion of the process doesn't really need to be done by a machine that's capable of becoming the primary node. So if you have many, many nodes in this replica set and many replica sets potentially, you may not want to spend a ton of money on all of those nodes, but you still want to be able to maintain this failover and election algorithm. So another a capability that you can configure into a replica set is to, instead of adding all secondary nodes to the replica set, you can also add what are called arbiter nodes. And as you might derive from the name, an arbiter node is kind of there to help with this arbitration process, the election process of who's going to become the new primary node if the primary fails. So the only thing that this node has to do is vote in the election. So you might have a bunch of secondary nodes, potentially a bunch of arbiter nodes, but the arbiter node will never become the primary node. It'll never be the target of that failover process, but it will participate in the election process in the event that the primary disappears. You see here, for example, that I don't have a replication arrow going from primary to the arbiter, just to the secondary node, and of course there could be many of those secondary nodes. So an arbiter node doesn't store data, which means it uses fewer resources, and it's really there to kind of maintain a quorum in the replica set. So quorum is usually the minimum number of participants you can have in a meaningful vote. So if you're working in a committee, you have to have some percentage of the members of the committee present in order to be able to vote, and an arbiter node sort of fills that role. So it responds to the heartbeat, and it also participates in the election of a new primary if necessary. As you can imagine from this rather simplified version of what a replica set might actually look like, managing and maintaining these different nodes in the cluster that's supporting a Mongo database can get somewhat complicated. And there are certainly sophisticated system administration tools and that kind of thing that you can use that might have a nice graphical user interface on them and so forth. But I want to also give you some ideas about how you can actually just do some of these management commands or create these clusters just with an ordinary shell script. It's hard to overemphasize the utility of being good at shell programming, and I'll try to give you some ideas about how to use the shell and a shell script to bring these nodes up and to take them down again. So let's talk about how do we initiate this replica set. First off, here's a shell script that is going to start a bunch of servers in this, well, just 3 servers, I guess, but that could be configured very easily. Some things to say about this shell script. First of all, the beginning here, the shebang or the sharp bang line at the beginning of a file is the mechanism by which Unix identifies the fact that this is a shell script. So it's just an ordinary text file that's out in the file system. And different operating systems have different approaches to figuring out whether something can be run or not. In Windows, for example, you have to look at the file extension. In a Unix system or Linux system, which I'll just use those terms interchangeably, there isn't really any kind of a convention for the suffix on the file or the file extension. Instead, the operating system has various ways of sort of introspecting the file and saying, does this appear to be an executable file? And in particular, if it sees that the first 2 characters of that file are a sharp and a bang, it'll treat the rest of that first line as a command to be executed in order to run this file, this shell script, as a program. So what's showing here is user bin env bash, right? So bash is obviously the shell or the interpreter for the shell, and it can run in a variety of different modes. Importantly, it can run in an interactive mode where it receives a command and then executes it, which is what you're used to using when you're running a shell in a terminal window. But it can also interpret an external script. And what's going to happen here is that when you try to invoke this particular shell script by typing its name at the command line, the shell that's running is going to look inside of here and start running a new copy of bash and hand to that new copy of bash the location of this file in the file system. And when bash starts up, when that new bash process starts up, it will recognize that it's being given the name of a command file to execute, and it'll load that in and start running the code inside of it. The other pieces of this sharp bang line, or what's usually called the shebang line, is I'm invoking this not by calling bash directly, but I'm using this other standard built-in Unix command called user bin env. What that command does is it creates a new environment in which that bash instance is going to be run, but it pays attention to things like your path variable in your currently running shell. So, for example, I could say shebang bash and be done with it, or give it a specific bash and hardwire that, maybe to say sharp bang /bin /bash or something like that. But that would mean that the script would always run that exact instance of bash. In many cases, what I find is that I'm going to have maybe a different version of bash installed, or I'm going to want to have some flexibility to run, instead of the standard system bash, which might be a little bit out of date if the operating system hadn't been updated recently, and maybe I have a local copy of bash that I want to use because it's newer, has some new feature in it. I can change my path variable to point to that version of bash before the path gets to the standard system command, and the bin env command honors that setting. It's going to use my current environment to start up the bash process that's going to run this script. And then the -x, you can also give bash command line flags in the shebang line. The -x basically says echo out the contents of the commands that you're executing as you're running them. That makes for a little bit more verbose output, but it lets you kind of keep track of what's happening as the script runs. You'll see here next that there's a function defined that we're going to invoke from below, and I want to come back to that and skip first of all down to the kind of the last portion of this script. It's illustrating the ability to do conditional expressions. So this if, then, else, fi is actually an if, then, else statement, as you might surmise. The if, the conditional that's being tested here, and there's several different syntaxes for conditionals in bash. This double square bracket thing basically says evaluate this as an expression, and if it's true, then execute the then part of the statement, otherwise execute the else part, as you might expect. Well, what's being evaluated in here? Well, this crazy $$ is a built-in shell variable, and as is the case with a lot of things in bash, they're unnecessarily brief. But the $ sharp sign is going to contain the number of arguments that have been passed to this shell script. So if that number is equal to 2, then what I'm going to do is I'm going to call this run Mongo function up here at the top with those two parameters. And you can access those parameters by saying $1, $2 to get the first argument and the second argument from the command line. On the other hand, if I invoke this shell script without any arguments, or other than 2 arguments, I guess it's not a very bulletproof check here for the argument count. But if I don't invoke it with 2 arguments, what's going to happen is that we're going to run the else portion of this statement. And what that's going to do is just start some default daemons. It's going to run that Mongo function again, or the run Mongo function, and it's going to pass in node 0 at 40,000, node 1 at 40,001, and Arbiter at 40,002. Okay, that's just kind of a convenience. So if I want to run an arbitrary MongoDB process, I can pass in the name of that process, as well as the port number that's going to be listening on. And if I don't want to do that, just sort of fire up kind of my default configuration, I can just type this script's name without any arguments, and it will do this. This weird fi here at the end is, yes, as you might have guessed, it's if spelled backwards. And again, that's one of the weird conventions in bash, that if you have a compound statement here with sort of several keywords that are connected together with arbitrary stuff in between them, there's going to be a delimiter at the end to signal the last line of that statement, in this case an if statement. And the way that bash does that is it spells it backwards. So there's also a case statement in bash, and at the end of the case statement you spell case backwards, so it's ESAC, signals that that's the end of the case. A little goofy, but you get to love it. Okay, so that takes care of kind of interpreting the command line, but now what are we going to do when we actually have figured out what to execute in terms of invoking this function? So again, here's the syntax: function run Mongo, and the function can be passed arguments. As you're seeing here, I can pass arguments that come from the command line to this bash script, or I can hardwire them into the script if I so choose. So what's going to happen here inside of run Mongo is it's going to be able to access those command line parameters with the same silly syntax of $1 for the first argument, $2 for the second, and so forth. So what I'm going to do here is I'm going to create a new Mongo process. But before I get there, what I want to do is I want to have these different Mongo daemons executing kind of in their own directories, because they're going to be configured to do some logging, and I don't want those log files to sort of overwrite each other. So the first thing I'm going to do is create a directory for each of those processes, and what's going to be used as a directory name is this first argument that gets passed into run Mongo. So I'm checking here to see, first of all, is that directory already present? So here's an if statement again. It goes from this if to this fi. And the expression that I'm checking here is actually -e, another very terse name for a comparator in bash. And what -e does is says, does this file or directory exist? And the one I'm checking for is the one at $1. So that would basically be looking for a directory whose name is the same as the first argument passed to this run Mongo function. So in the case of, say, this run Mongo invocation, I'm going to look for a directory called node 0 in the current working directory. What I'm actually interested in, though, is not determining whether such a directory exists, but whether it doesn't yet exist, in which case I'm going to create it. So to negate the sense of that check, to say, hey, I want to know if this doesn't exist, you can use what's a familiar negation, logical negation operator, the exclamation mark. And then if that directory does not exist, I'm going to create it by running makedir, and I'm going to pass makedir that path to the directory I want to create. And a flag that's useful in makedir is -p for path, I guess. What this will do is if you pass in to makedir a /separated argument, instead of just saying makedir foo, which would just make a directory called foo in your current working directory. If you wanted to kind of create an entire directory structure, you could say makedir foo/bar/baz, and that would actually create a foo directory. Within the foo directory, create a bar directory. Within the bar directory, create a baz directory, all in one step. So that's what -p does. As an aside, if you know something about makedir-p, one of the things that this will do is if you ask it to create a directory that's already there, it'll just comply and say, oh, sorry, it's already there, and then just exit successfully. So in fact, we could just say makedir-p $1 and not have to use that conditional, but I did want to just have another opportunity to illustrate some other capabilities of that conditional statement in bash. So now that the directory is present, we can actually start up the MongoDB daemon. And one of the things I like to do when I'm faced with a command that's going to take a lot of command line arguments is to separate them on separate lines within the file. Just kind of makes it easier to sort of figure out what's going on, what all the arguments are, how they pair, that kind of stuff. But in order to do that, I've got to tell the shell to treat these all as if they were a part of a single command. And what you do then, or what you do to indicate that, is you end each of these lines with a backslash. So it's essentially saying, yeah, I know there's a new line coming up, but just ignore it and treat the next line as if it's part of this same line. So it's just a way of expanding the command out onto multiple lines. So the arguments that are being passed here, first of all, the replica set has to have a name. We're creating one replica set, and I've just chosen to call that cos343. We need to give it a path to the location where this particular instance of MongoDB is going to store data. And for that, we're going to use $1, right, which was this first argument that got passed into the run mongo command. We also want to tell it what port to listen on. Because we're doing this all on the same physical machine here, just to illustrate these ideas, I've got to have each of those processes listening on a separate port, because I can't have multiple processes listening on the same port. And that's what this second argument does. So these three different nodes in the replica set that are going to get started up are going to be listening on those three different ports. Small files is just kind of an optimization. Fork says create a new sub-process here so that you don't end up waiting for that MongoDB process to exit. We're specifying a path for the log file that MongoDB is going to create, and I'm putting that inside, again, of this $1 directory in a file called mongodb.log. Again, that's a really common suffix for log files. And then log append says add new logging output to the existing log file if one is already there. If you don't specify that, it will create a brand new log file from scratch whenever the MongoDB process fires up. So again, to summarize what's going on here, the run mongo function is doing the construction of each of these MongoDB servers, and this if statement here at the end is basically just interpreting the command line arguments. So again, we can do one of two things, or this is intended to be used one of two ways. Either we invoke it with no command line arguments, in which case the if clause or if returns false, and we start up these three processes just as kind of our default configuration. But if we want to, we can also pass in the corresponding arguments for the directory name and the port number to run Mongo arbitrarily from the command line. Having started up those servers, we can also have a script that will shut them down, right? We've got potentially, well, the default is to have three processes running, each of which is going to be a separate instance of MongoDB. If we want to shut those guys down, we could either, kind of hunt through the process list and kill them off manually, or we could write a shell script for it. Again, same deal here. I'm using, the shebang line to run the bin env command, which interprets the current environment in which this script is run, and then invokes bash-x, passing the name of this very file to bash so that it can be executed. It turns out that when you run Mongo, in the directory where you've specified, or the directory that you specified as the DB path here, in our case, say /node0, when Mongo starts, it's going to create a lock file just to indicate that it's doing something with the contents of the data in that directory. And that file actually contains the process ID of the MongoDB server process that's been started in that directory. So I can kind of just use that fact to implement this shutdown script. What I'm going to do then is iterate over these lock files. So the for conditional. Actually, I said before that we always end with the reverse of a keyword. For has a slightly different syntax. We say for and then some list of values, do, and done at the end. So this is a for loop. It's kind of closer to a for each loop or a for variable of array kind of a loop in JavaScript, for example, in that it's going to expand this shell wildcard, right? So /star, right, is going to say, give me all the directories in the current working directory and go look for a mongod.lock file in each of those directories. So if we had just started up these MongoD processes with the previous script we looked at, we're going to have a directory called node 0, node 1, and Arbiter, right? Those were the three values that got passed in by default. And when the MongoD starts up in those three locations, each of them is going to create a mongod.lock file. So what this is going to do is basically expand to ./node0/mongod.lock, ./node1/mongod.lock, and so forth. And then the for statement is going to iterate over these commands in the do-done block, assigning PID file, process ID file is what I'm intending there, to each of the values that this shell wildcard expanded into. Now what I want to do is not use the file name. I want to get at the actual contents of that file, which is going to contain the process ID that I want to stop. So what I'm going to do is use this subcommand syntax here. You say $paren and then a close paren at the other side. And what that does is asks bash to run the command enclosed between those parentheses and return as its value the output from that command. So what I'm doing is just concatenating the contents of that PID file. That's going to contain a process ID, and the result of the $paren thing is going to be that the process ID that was read from the file is going to be assigned to this new variable PID. Now, you notice here that there's a $sign ahead of the PID file, not a $sign up here where it's declared. The idea here is that when you declare a variable in bash, you do it without the leading $sign, and when you want to refer to that value, you mention it with the leading $sign. So PID file is the name of the variable that's going to be assigned by the for loop, but $PID file is going to be the current value of that variable. And that's what we want to get at, right? We don't want to cat out a file called literally PID-FILE. We want to cat out a file that has a name specified by the values that we're iterating over in the for statement. So PID is now going to have the process ID of one of those lock files. I'm going to then check to see if that actually worked properly. So here's another example of a different type of conditional you can do. I'm doing a simple string comparison against an empty string. So if for some reason that cat operation didn't work, or the block files were empty or something like that, I would be comparing the value that was read with the empty string. Remember, I assigned the value to the variable PID, and if I want to refer to that value, I use $sign to get at the value in that variable. So I'm basically saying, as long as the PID file, or as long as the PID is non-empty, I want to do this command. And then the business end of this thing basically is here. We're going to use the kill command. This is a standard built-in command in Unix that is used to stop an existing process by its process ID. So we're saying kill that particular process ID. Notice the $sign because I want to get at the value of the variable, not the variable name itself. And then the second argument here, -2, there's different signals that we can send to different Unix processes. Kill -9, for example, is kind of a last ditch effort to really stop a process. It basically means kill this off with malice aforethought and really try hard to get rid of that process. Kill -2 here, and this is kind of specific in a way to the MongoD process in that it uses that signal that's going to be sent from our shell script to kind of ask it to shut down in an orderly fashion. So if it's got files open, they'll be closed, and then the process will eventually shut itself down. So that's the reason we're passing that -2. Again, another example of how to use a shell script to do kind of a common, tedious, potentially error-prone operation. Again, also, in a production context, we would be using more sophisticated process management tools, but for our purposes here, and this is something that you encounter over and over and over again in a development context, it's really convenient to be able to define a shell script that does these little kinds of jobs just to kind of make your life easier and more reliable. You're not going to find, can't open this process because somebody else is already listening on this port, those kinds of annoying error messages that you get when you sort of try to do all these things manually. So learn the shell, learn how to use it, learn how to do some of these basic operations. It just kind of makes your life as a developer less painful and arguably more productive, right? You're going to get more things done more rapidly if you can have some assistance from the shell. All right, so we have an ability to fire up our replica set and to shut it down easily. Let's actually configure the replica set itself. So first of all, we're going to use, let me go back to this configuration here. I've got node 0, node 1, and Arbiter listening on ports 4000, 4001, and 4002. So that's going to be the port number is going to be the way that we're going to differentiate one of these from the other. So here, I'm going to basically be connecting to the process that I've called node 0 that's listening on port 4000. And you can see here in the output from this command, that's kind of verified for us that me here is the host and port number for the process that's responding to me in this little MongoDB shell operation. So we're talking to process ID 40,000. And the command that we've issued to it is rs.initiate. So rs, which stands for replica set, is another one of these kind of predefined variables that gets set up for us by the Mongo shell and provides us with an interface to the replica set operations that are defined in the shell. So the first one to kind of get this kicked off is called initiate, and that basically says, okay, we're going to start doing the replica set thing, and the first node that we're going to have in that replica set is going to be this one that we have given this command to, the one that's listening on port 40,000. Just to clarify, when I issued this command, I would have run Mongo shell and specifically connected to the process listening at 40,000. So just like you've been connecting to the default process, for example, listens at 27017, you can specify the particular host name and port number that you want to connect to when you run the Mongo command. So that's what I would have done up here before I issued this command. I would have connected to localhost :40,000, and that's why we see this particular host and port number responding. Okay, so that basically starts the replica set and adds node 0 at 40,000 to the set. Now we want to add more nodes to the replica set. So I'm going to do rs add, and then here's my host name and port number. I'm issuing this to the same server on port 40,000 that I was accessing back here. So here I connected to port 40,000 process, initiated the replica set. I'm still connected there, and now I'm issuing another command to add a node to the replica set. And Nurkbook is just my local host name, and 40,001 is the is the port number on which that second process is running, the one that I started back here that I put into the node 1 directory. So the add command adds another node to the replica set. So I've created port 40,000 is where the primary node lives. Port 40,001 is where a secondary node lives. And then I'm going to add an arbiter as the third node of the replica set. So you've got to use a slightly different command here to the replica set to say add an arbiter, and then again give it the host name and the port number where that MongoDB process is listening. And that's again the one that I started up by default back here. And you can see in both cases we get back an OK of 1 to indicate that everything worked fine. Now having done that, I'm going to ask again, I'm still on the port 40,000 MongoDB, I'm going to ask it to give me some information about the kind of the master, which host is kind of the master host, and which are serving other roles, the primary and the secondary. So the response from this is a list of hosts, and we can see here that 40,000, 40,001 are the two hosts that are listed as part of this set. And then there's, oh, by the way, also an arbiter that's configured listening on port 40,002. And we can see the name of the set and so forth. The key thing here, and the reason that this function call is master, is it tells us true that the instance of MongoD that I'm accessing here, the one listening at 40,000, is in fact the master, the primary node of this replica set. It is not a secondary node, and it sort of mentions itself as its own primary node, and it mentions that it is NERCbook 40,000. If we ran this on a different node, one let's say the secondary node, then these values would be changed accordingly to indicate that the actual primary node is the 40,000 port and so forth. So this is just kind of a way to verify the setup that we think we have is in fact what we've got. We can also do, so this is issued to the DB object, kind of a top-level, high-level overview of the configuration of the replica set. Back on this page, we can see that we can get a little bit more information from the replica set itself. So we're issuing this on the RS object and asking for its status. So we get things like the set name and then the members of the set. So this is really kind of the key portion of this. We can see that we have some IDs again for each of these. You can see that the same convention is being observed as for creating new data in the system. But the part that we're interested in seeing here really is the name of the replica set, excuse me, the name of the node in the replica set, and then it tells us is it healthy, 1 or 0. In other words, as far as the replica set is concerned, we're getting a heartbeat signal from this particular node, and then it also has this state string that, and well, state and state string. So you can get a numeric state or you can get a string valued state. One might be easier to use in code and the other might be more helpful as when you're looking at it as a human. And we can see that the one at 40,000 is the primary node. The one at 40,001 is the secondary node. And then we get this additional piece of information that says who am I syncing to? So the secondary is syncing to the primary in this case. And then we have a final one, state 7, which indicates that the process that's listening at port 40,002 is an arbiter node. All right, so let's take a look at how we can get some evidence that this replication process is actually working. And I want to show the process here where I'm running on node 0, the 40,000 one. So I've made a connection using MongoDB shell to the node that's listening on port 40,000. And there I issue the standard insert command, right? db.books. I'm going to create a books collection and I'm going to add a new document to that collection that just has this simple title and the name of a book. And we get a result coming back saying that we inserted one thing. And then I can just turn and run right away and list all of the books that are available to me from node 0. And you can see that that's the output. Now, I also want to see whether or not I can fetch that same value from node 1, the process that's listening on port 40,001. So in order to make sure that I'm getting to that guy, I'm going to run the Mongo shell, except I'm going to specifically say, instead of connecting to NERCbook 40,000, I'm going to connect to NERCbook 40,001. So when I issue the request, it's going to be responded to by that particular node, which as we've just seen is configured as a secondary node. Now, if I try to do that without any other operation here, it's going to fail. The reason being that the default configuration for a replica set makes all of the nodes in the replica set basically read-only nodes, other than the primary one. So the secondary nodes are there strictly to replicate data from the primary node. If you send a request for data to the secondary node, it's going to just say, sorry, that's not my job right now. So but on the other hand, if you want to sort of improve the performance when you're reading data from the replica set, you can authorize the secondary nodes to also respond to requests to gather data. The way that you do that is illustrated by this first command. So from the database, you get to the Mongo instance itself, and call this function setReadPreference and set it to secondary. That just says basically, hey, it's okay to allow reads from those secondary nodes. And at that point then you can say db.books.find.pretty, and that gives us back exactly the same response from node 1 that we got back here from node 0, right? Same object ID, same title, and so forth. So obviously we inserted that record here on node 0, and behind the scenes it managed to be replicated to node 1, because when we went to node 1, again connected via Mongo to node 1 specifically, we can read the same information. Let's now take a look at this failover election process. I'm not going to physically go and clobber the process that's running Mongo. Instead, I'm going to just shut one of these instances down, one of these nodes. So I'm going to connect to node 0, the one that's listening on 40,000, and I'm going to issue in that node db.shutdownServer. That's going to just do a nice smooth shutdown of that server process, and we can see some output that we get from the other servers. Shows us that there's something weird going on here, right? We see here that we can, when the server shuts down, our Mongo shell starts freaking out, right? I can't connect to the thing that's listening on port 40,000 because it's no longer running. So we've succeeded in shutting down that node. But that's going to potentially cause a catastrophe, right, for the other two nodes. I've still got a secondary node running and an Arbiter node running. And what I want to do is just show you how we can kind of observe the process of electing a new primary node. So the next thing I'm going to do, and now I'm connecting to node 1, the 40,001 server, and I'm going to run that same rs.status command that we saw before. And we can see there's some fairly substantial changes going on in here. In particular, for node 0, the one that was listening on port 40,000, we see that its health value has gone to 0 and that its state has been switched to state 8, which means either I can't reach you or there's something goofy going on there. So node 0 is out of the picture here. On the other hand, we can see there's also some changes for node 1. In particular, well, it's still healthy, but its state has now been upgraded to primary. So between the time that we last ran rs.status from node 0 and then shut down node 0 and now are reading rs.status from node 1, there was plenty of time for the heartbeats to be detected as failing from node 0 and for the election process to go on between node 1 and the Arbiter node. In that case, there's only one node that can possibly become the primary, so it was kind of easy to choose node 1 as the primary, and that's reflected here in its state. And then the Arbiter node is still there, fat, dumb, and happy, listening for the heartbeat from node 1. Again, it's important to note that although we went and manually shut off one of the nodes in this replica set, that our client programs are unlikely to have noticed that anything happened. They could have sent requests immediately after the election process was complete, and node 2 would have now been elected to be the primary node and would have happily served information for reads or writes to the database, and our client code would not realize that anything was different. Okay, so now that we've seen the failover take place, let's turn on node 0 again. So the shell script we looked at earlier, which is actually called startReplicaSet.sh, I mentioned that I can pass in parameters on the command line, which will start up a new MongoDB server in that directory on that port. So that's what I'm doing here. Basically just running exactly the same MongoD command that I ran previously in order to restart node 0. And we get some information here about how that process went. But now let's go look again, and I'm going to connect to node 0 to show that it's actually running. And from there, I'm going to issue the rs.status command. And let's inspect this output. You can see we still have 3 members, but node 0, right, the one that's listening at 40,000, has now been designated a secondary node, right, because we had already elected node 1 as the primary node previously. So we don't try to swap the previously stopped node back in as the primary node. The secondaries and primaries are designed or are intended to be pretty much of equal capability. So we've already switched everything over to the node at 40,001. It's performing the primary services just fine. We're going to then make node 0 a secondary node to back up the previously elected primary node. And then the Arbiter node is still there serving its purpose of recognizing the heartbeat and doing elections as required.